Welcome back. We're in the middle now of reviewing the final part of Unit 1, which is the topic of static equilibrium and torque. So the last couple of classes we've reviewed, or last couple of sessions I should say, last couple of topics, we've reviewed forces in general with a bit of stuff from Physics 2204, and we've also taken a look at the idea of static equilibrium. And static equilibrium, you should remember, means that the object has no net force acting on it. That's one part of it. But the other side of it is there can be no net torque as well. Because in order for an object to be in a condition of static equilibrium, it cannot be moving. It can't be sliding, which we call translational movement, but it can also not be rotating, which we call rotational movement. And the only way for that to happen is therefore to be no net force, which means no sliding, and also no net torque, which means no rotation. So let's take a look at torque. And this should really be just review for you because you've done all this before. So let's take a look at what torque is. So in our last unit, like I just said, we studied the translational movement, the side-to-side stuff, or the lack of side-to-side motion because of no net forces. So now we're going to take a look at rotational movement and what is needed to first of all cause it and then to prevent it. Well, you may remember from the last lesson that we took a look at a seesaw, okay, a mom and her son on a seesaw. And if you take a look at the picture there, you'll notice that the mom, right here, and her son over here are about the same distance from the pivot. And the mom has a bigger force, 500 newtons of force of gravity, and the boy only has 200 newtons of force. So obviously this seesaw is going to start to rotate because the mom is going to move downwards and the boy is going to move upwards because he's lighter. And that just makes sense. Okay? Common sense would tell you that. Now there's no net force here because you'll notice the sum of the two downward forces, 500 plus 200 is 700, and the upward force at the pivot is also 700. Now that's assuming that the seesaw itself is weightless. And we can assume that it has such small amount of weight that it's not going to be really relevant here in this case. So because the mom is heavier than the son, the seesaw will start to rotate. Left end will go down, right end will go up, and we call that counterclockwise because that is the opposite direction to what the hands on a clock would do. The hands on a clock go clockwise. In other words, they rotate from left to right. Okay, in other words, they go this way. That's a clock. Okay, so counterclockwise is the other way. So this side comes up, this side goes down. So that's a counterclockwise rotation. And because the seesaw is rotating like that, that tells us that there is torque. Okay, a torque is a rotational force. Okay, it's a force that causes rotation. And that's what's happening in this picture. Now, if the mom wants to balance the seesaw, in other words, she wants to play with her son and balance the up and down motion of the seesaw, she has to move. She can't sit at the end and the boy sit at the other end. That doesn't work. Okay, so what's going to happen is the mom is going to have to move in closer to the center. Okay, and that just makes sense. Okay, she's going to have to move in closer here. The boy stays where he is, and then if she does that, and you may have done this yourself sometime, like playing with a small brother or sister, or you may remember when you were young and one of your parents playing with you on the seesaw. And by sitting in closer to the pivot, that seesaw can now balance. Now that tells us that there's two things that affect that rotation. Okay, there's two factors that affect torque, in other words. There's force, obviously, as part of it, the amount of force, but the other side of that is the distance from the pivot point. So if we look at this, we've got 500 newtons of force and 1 meter of distance. And you'll notice if you multiply the two of those together, it equals 500. On the other hand, the boy over here only has 200 newtons of force, but there's 2.5 meters of distance. Multiply the two of those together, and you get 500. So same, both sides, right? That quantity is called torque. That quantity is called torque. And what's happening here now, the mom is causing a counterclockwise torque, because if the boy wasn't there, the mom would make the seesaw rotate counterclockwise. The boy is causing a clockwise torque because if he was the only one on the seesaw would rotate clockwise. So in this case, they're actually balancing each other out. So in other words, the net force would be 0. Okay, so that's what we call torque. And the symbol for that is this Greek letter tau. Kind of looks like a fancy looking letter T. But anyway, to distinguish between clockwise and counterclockwise, we just use CW for clockwise. This is just a convention. You can use something else if you want, but that's normally the way it's done. And CCW for counterclockwise. That's how you distinguish between them. Okay, some people actually use like a little circle with an arrow on it, but normally that's the way it's written. And by the way, another name for torque is moment of force. Okay, it's the same thing. Really, a torque is a rotational force. It's a rotational force. So in general, the torque is just by definition R times F, where R is the radius or the distance that the force is from the pivot point. In other words, if you measure the distance from the location where the force is applied to the point where the pivot is, that would be called radius or distance. And we use an R for that. And then we put an F in there. Now, that F, it turns out, is actually perpendicular. The force has to be perpendicular for this formula to work. And if the force is not perpendicular, we have to make it perpendicular. And we make the force perpendicular by saying F sine theta, where theta is the angle between the object and the force vector. And we'll look at some examples of that now in just a moment. So now then, we have two conditions for static equilibrium. There's two things that had to be met. Number one, and that's what we did in the last lesson, the last topic, static equilibrium forces. So the net force has to be 0. So in other words, the sum of the x forces, in other words left and right, have to equal 0. And the sum of the vertical forces up and down, or the y forces if you like, also has to equal 0. In other words, no net force at all. And the second condition that must be met, and this is what we just talked about, is there can be no net torque. If there's any net torque, then that condition is not met and we don't have static equilibrium. It's that simple. So in other words, the sum of all the clockwise torques and the sum of all the counterclockwise torques have to be equal. They have to balance. Otherwise, if they're not, the object would rotate. And if the object rotates, we do not have static equilibrium. So you've got to watch for that. Now, it is also possible to move the pivot point. Okay? Like with a seesaw, the pivot point is pretty obvious, right? The pivot point is where the hinge is, and the seesaw tips back and forth at that pivot point. But the pivot point doesn't always have to be there. In other words, we can actually move the pivot point for the purposes of calculating torque. We can pick any pivot point at all. Okay, that's like a real pivot point right there, but we could put the pivot point at the end if we wanted to. And there's times when doing that has an advantage. And the reason that it might be an advantage sometimes is any force that is acting directly at the pivot point will cause 0 torque. Now that's useful if, for example, you had two unknowns in the equation. You could put your pivot point at one of the unknown forces, and then that would cancel that one out from the calculation. You wouldn't need to worry about it. And we're going to do some examples like that over the next couple of lessons. So if you're not exactly sure what that means, then just bear with me for a little bit and you'll see examples of it in a minute. Now, like I said, a lot of times the natural pivot point is obvious, but other times it's not so obvious. Like sometimes you have objects that really don't rotate anyway. Like you might think of a diving board, for example. Diving board doesn't really rotate, but if one of the supports let go, it probably would. But it would depend on which support let go, because a diving board generally has two supports. So depending on which one let go, which one broke, that would cause a different rotation of the diving board. So the natural pivot point may not always be obvious. Okay, so we can move our pivot point around as we need to in order to make the problem easier to solve. And you'll see examples of that, particularly in the next lesson, in lesson 16. But I'm getting ahead of myself here. So let's take a look at some examples then from old publics. And there's lots of examples of torque calculations. And most of these examples would be considered to be level 1 questions. In other words, the most easy question of all. Generally, it's calculate the torque when you're given the distance and the force, which is pretty straightforward. Like, for example, in this first one, torque, which is that symbol, letter tau, is R times F, distance times force. Now, this force is perpendicular, so I don't need to worry about sine theta or anything like that. We'll get to one of those in just a minute. So all I have to do is take my distance, 2.0, multiply it by the force, 14 newtons, and that will give me exactly 28. And because I'm multiplying force by distance, my units are just newtons times meters, or newton meters. So the answer obviously is D. The second question there says, which condition will produce rotational equilibrium? In other words, what condition has to be met if the object doesn't rotate? It doesn't turn around. Well, that would be no net torque. So that would be this one. The net torque has to be 0. This guy right here, F net equals 0, choice A, that is for translational equilibrium. And you put A and C together, and you get static equilibrium. Like static equilibrium is a combination of rotational and translational equilibrium. Static equilibrium is both of them combined. But we can just have one or the other. It's possible for an object to be spinning, rotating, and not sliding from side to side. Like, for example, if you turned your bike upside down and spun the tire around, okay, we wouldn't have rotational equilibrium because the tire is spinning, but since the bike is not going anywhere, it would still be in translational equilibrium. So it is possible to have one without the other. But when you have both at the same time, that's when you have static equilibrium. The last question on this page says, which one of those best defines torque? In other words, which one of those would be the proper units for torque? And you already know what that is because we just talked about that in the first question on the page. It's newtons times meters, right? Distance times force, or force times distance. That's how we calculate torque. Therefore, that's the units for torque, and that would be the best definition of it, right? The definition of torque is it's the product of the distance and the force. The force that's applied and the distance of that force from the pivot point, what we've chosen as the pivot point. So let's move on to another screen. Okay, this one would be more of a level 2 question. What you need to realize here is you're looking at which one of these forces would give you the smallest amount of torque. The smallest torque. Okay, well think about this. Remember that torque, when there's an angle, torque is equal to Rf sine theta. Now when you think about sine theta, the maximum value that sine theta can have would be 1. So if sine theta equaled 1, theta would have to be 90 degrees. In order for sine theta to equal 0, theta would have to be 0 degrees. So obviously, the minimum torque would be when the angle is 0. The maximum torque would be when the angle is 90. So this one here, that's the maximum right here. And this is the minimum right here. So that what that tells you is that the smaller the angle between the force and the object, the smaller the torque. If you want maximum torque, you apply the force at a right angle. But that's not what this question is asking, is it? This question is asking for the smallest amount of torque. Well, the smallest amount of torque would be the smallest angle. And if you look carefully at this diagram, there's the smallest angle right there on A. So A would be the smallest torque. B would be the largest torque. And then C and D would be somewhere in between. B would be the largest because it's a right angle. You can see that there. A has the smallest angle. And remember, you always measure the angle from the object itself, between the force vector and the object. So A would have the smallest possible angle in that diagram between the choices of A, B, C, and D. So the answer is A. Now, what is torque? Now, you got to be careful. Torque is R times F, but very specifically, remember what I told you back a couple of screens, RF perpendicular is the important thing. If the force is not perpendicular, you would have to say this up here, RF sine theta. That's not one of the choices, however. But RF perpendicular is. So that's the right answer. Now be careful, okay? Don't choose that one there because there's something missing in that one. And I'm hoping you can see what's missing. Okay, if you compare that to the expression I wrote up at the top of the screen, you'll notice that it's the force that's missing. There's no force in that. In order to have torque, there has to be a force and there has to be a distance from the pivot. So for this one, that's the right answer, RF perpendicular. Okay, let's try a couple of more. This time, you're asked how much torque is produced by that 75.0 Newton force exerted on that wrench. Well, again, the pivot point is pretty obvious. There's the pivot point right there. The nut that the wrench is trying to turn would be the pivot. That would be the natural pivot. It's pretty obvious where it is. You're given the distance from the pivot to the end, which is where the force is being applied. You're given the force itself, and you're given the angle. So I can say torque is equal to RF sine theta, which means I say 0.35, and I'm going to leave out the other 0 just for space reasons. 75 newtons, it's actually 75.0, right? So there's going to be, if you look at the numbers that you're given, there's going to be 3 sig figs in our answer. But I'm just going to write them without that extra 0 because it just makes it a little bit more compact. And I don't have a whole lot of space around the screen to write. So if we do that calculation on your calculator, you will get 15.8, which means the correct answer is A, 15.8 Newton meters. If you use cosine instead of sine, you would have gotten a different answer. Okay, if you divided by the angle, you would have gotten another one of those answers, and that's where all those other choices came from, by the way. What is the ability to turn a body around a pivot? The second question there. Well, that's an easy one too, because right now we're dealing with torque, so that's a pretty good clue there. But that is actually the definition of torque. That's what we call a definition of torque. The ability to turn a body or an object around a pivot point. That's called torque. It's a rotational force. A rotational force. Okay, then we got another one on the bottom just like the one on top, except there's no diagram, but it's still the same calculation. We still say RF sine theta. Okay, so we plug our numbers in. We're given all those values. 0.800 actually, but like I said, for space reasons and simplicity, I'm just going to leave out the zeros. Just remember to put the right number of sig figs at the end, that's all. 25 newtons is my force. 30 degrees is my angle, so I say sine of 30. And I do that calculation, it equals 10. Now, because there's 3 sig figs in all these values, I would have to say 10.0. So the answer would be A. And that one is done. Okay, so you can see there's a whole variety of questions that you may see on your public exam related to torque. But I can guarantee there's probably going to be at least a couple. All right, let's take a look at this next question. Now, this time it asks, where would the greatest amount of torque be? Now, remember what I said to you a few minutes ago. The greatest torque is when theta equals 90. In other words, when the force is perpendicular to the object. And that, very obviously now, is A. Okay, there's actually one case there where there's no torque at all. Okay, and that would be this one right here. This one here has no torque. And the reason there's no torque is because the angle is 0 degrees. And the sine of 90 is 0. So therefore, RF sine theta would give you 0 torque. Okay, and it's obvious. I mean, if you pull on the end of that lever like that, okay, nothing's going to move, is it? Nothing's going to rotate, so there wouldn't be any rotational force there. It has to be at an angle. Then we've got the last one there. What torque is provided by that massive person? Now you got to be careful now. A person standing on a diving board is going to introduce or going to exert a perpendicular force, so we don't need to worry about the sine theta. You can put it in if you want, but just put an angle of 90 degrees in there. Okay, so if you like writing it down as RF sine theta all the time, you can do that. You can still do that. But you need to put in sine of 90. Okay, and the sine of 90, remember, is equal to 1. So it doesn't change anything. So the distance is 1.4 because that's the distance from the pivot. Now the force here is actually the force of gravity. And remember, gravity is mass times 9.80. So if you do that calculation, you will get 823 Newton meters, but you're only allowed to have 2 sig figs because of this number right here, the 1.4 meters. So therefore, you would round that 823 off to be 820. But it's obvious that, I mean, when you're doing multiple choice, significant digits you don't have to worry about so much, because in multiple choice, obviously, the right number of significant digits are already going to be there for you anyway. So it's not something that you're going to have to worry about too much. All right, let's try a couple of more. In this one, very similar to the lever one that we just looked at on the previous page, in which situation would the greatest torque be exerted on the bolt? Well, in the first one is obviously no good, because if you're trying to turn that wrench and you're just pushing in on the nut, that's not going to cause any torque at all, because right here the angle is 0. So that means that the torque is also 0. So that wouldn't be the greatest torque for sure. That's 0. That's no torque. So we can eliminate that one right off the bat. Now in the other 3 choices, the forces are all perpendicular. Okay, all these forces are perpendicular. You can see that by looking at the diagrams, right? So that means that we got the maximum angle. So that part is okay. So the forces are the same though. But they're not the same torque, because if you look carefully, the distances are different. The point where the force is being exerted, it's right here, right in close to the nut. So there's a small r right here, a small value of r. In this one here, the second one, there's a medium value of r. And in the last one, there's a large value of r, the largest one. So obviously then, because torque depends on 2 things, both distance or radius and the force, in this one, because the forces are all the same, it's the distance that's going to be the determining factor. So the largest distance would be the largest torque. So the answer is D. The answer is D. Next page. Here's another one. Which one of those forces in that diagram would give you the largest torque on the lever arm? Now these are a little hard to pick out. That's A, that's B, that's C, and that one is D. So again, you look at this angle here, 30 down here, that is totally irrelevant in this case. We don't need to worry about that angle, because it's the angle between the object is the one that's important. So there's the one that's important right there. That's the perpendicular one, and remember, the perpendicular one is always the one with the maximum torque when all the forces are in the same location. So the answer would be A. It would definitely be A. The last one on this screen. We've got a 4 Newton force that's applied tangent to the outer edge of a bicycle wheel. Now it would be useful here to actually draw that. Here's the bike wheel. Okay, here's the force being applied at a tangent right here. Here's the radius right there. So that's your object, in other words. Okay, there's your radius. There's the center of the wheel. And remember, that's the pivot point for a wheel, obviously. The distance away, the radius is 0.50. The angle is 90, so it is a perpendicular force. So all you have to say here is RF. Now, if you want to say sine theta, like I said, be my guest. Just remember to put 90 degrees in for theta. And the sine of 90 is 1. That's why when it's a perpendicular force, I tend to leave it out. But you can put it in if you want. If you want to remind yourself that sine theta belongs in the equation, then by all means put it in all the time. And just say sine of 90 when it's a perpendicular one. So all we got to say here is 0.50 for R, 4.0 for force, and 0.5 times 4 would equal 2.0. And that one is done. And we've got one more screen to take a look at before we're done. Just one more example. And this time it's a pretty straightforward one. And like I said, every single one of these questions have come from old public exams. If you go back and look at the old publics, every one of them will have at least 1 or 2 questions on torque like this, like similar to the ones we're doing here. So it should be easy marks. These are really not that bad. Torque equals RF perpendicular, right, because it is a perpendicular force here. The R is given. It says from the hinge, so the hinge obviously is the pivot point of the door. That makes sense. And the force that's exerted is 80.0 newtons. Multiply that and you get 120. Now, the numbers that you see there are written in scientific notation. So you need to remember that 120 is the same thing as 1.2 times 10 to the power of 2. Okay, so sometimes the answers will be written in scientific notation like that. So if you can't quite remember how that works, all you got to do, remember, is take the decimal point, move it between the first and second digits, 1 and 2. So to do that, I would move 1, 2 places. So that's why I say 10 to the power of 2. 1.2 times 10 to the power of 2. That's that answer right there. Okay, and that concludes the lesson on torque. Now what we're going to do in our next lesson, lesson number 16, which will also be the last lesson in Unit 1. Okay, then later in the week we're going to move into Unit 2 in the course. But the last unit, or the last topic, sorry, in Unit 1 will be problems that involve balancing torques. In other words, more than one torque being applied to an object at the same time. And we're going to have to determine, for example, maybe what force is needed to balance, or you might be asked where should the force be applied in order to balance, those types of things. Okay, so we're going to stop right here. Again, good luck with your study. Work hard, and the test will not seem nearly as difficult as you might think. So be sure to join me again when we talk about balancing torques in topic number 16.